So welcome all to week 1 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IIT Bombay, and I will be taking this course run every Tuesday 6 to 8. Okay. So first of all, I'd like to tell the topics that I plan to cover today. Okay. I'll briefly go over some vector algebra that would basically involve very basic calculations related to vectors, which is vector addition, vector multiplication with a scalar or dot product, etc. Then I'll go to norms. Then I'll talk about angle between two vectors. Okay. And then I'll move to some matrix algebra. Towards the end of the lecture, I'll cover some questions related to vector space, subspace. So we'll define what a vector space is. We will see what a subspace is. And we'll talk about basis and dimension of these quantities. So we'll calculate some basis for some of the vector spaces, and we'll also calculate the dimension for those vector spaces. Okay. So for the initial part of the course, I have taken a tutorial for this course earlier too. What I feel is that these three books are very good resource if you want to learn out of this course. So apart from the course, if you follow any one of these three books, it would be very great. Okay. And not only for this course, that is Essential Mathematics for Machine Learning, even if you want to understand linear algebra as a whole, these books are very good. Okay. So I have arranged them in order of their rigorness. Okay. So this book is sort of elementary if you don't have any exposure to linear algebra. Okay, you are not from a mathematical background. You can start with this particular book. Yes, the first one is good for absolute beginner. Okay, so this is Linear Algebra and its Application by David Sillay. I came across this book when I was doing my bachelor's from DU. So yeah, so this can be a very good resource to start linear algebra. This is slightly more rigorous than this, but if you have done linear algebra at some part of your life and you have forgot, then you can go for this book also. Okay, this would help you brush up your memory. And the last one is my favorite book, but it is little bit more mathematical. This is Linear Algebra by Fredberg and Inson. So this is a very good book. You can, I think, download PDF or you can buy these books online. So the first one is basic, and this one is more mathematical. You can go for any one. Okay. Okay. So the course is called Essential Mathematics for Machine Learning. Now, based on my experience, if I say what all maths are being used in machine learning, today a variety of topics are being used. But if you talk from a course perspective, I think this course would cover linear algebra and some calculus. Okay, this is going to be the overall flavor of the course. So let's let's ask us first question that what is the first step in machine learning? Like when you hear about machine learning, when you do machine learning, if you have some prior knowledge to machine learning, what is the first step that someone does in machine learning? Let's say you want to create a model or you want to perform some tasks using machine learning. What would be the first step that you want to do? Like you can type it in the chat box. What do you think would be the first step uh, in the machine learning thing? So if you want to create a model or you want to do something, what would be the first step that you want to do? Yeah, get data, exactly. So when you get data, for those who are not aware of machine learning, so you have some data and then you try to learn some pattern from that data. Okay. Okay. So how do you store some kind of data? Let's say I am Pintu. So how would my data look like? So my data might look like my name, right? Then my age probably, and other things. What are my educational qualification, height, color, and those kind of things. Based on this, someone might want to take this data and learn something on this. Not only one data, but a bunch of data and learn something on it. Okay. So if you see, when we write data, we always write it in form of a vector. Okay. So this representation, like if you represent a data point, you have many characteristic of that particular data point. And when you represent that, you always represent that in form of a vector. Okay. So this is why understanding basic operations on vectors become important when you talk about machine learning. Vectors are sort of elementary parts of machine learning. So if you have any doubts related to vector, how do they work, this is the best time to clear in today's class. And then it would be okay for you to build up on that. Okay. So vectors, what are vectors? So vectors are a one-dimensional representation of data. I would say, I would just talk, this is a very layman language, where you don't have just one value, but you have more than one value arranged in a single dimension. Yes, these notes will be shared. Okay. So we'll talk about some basic operations on vectors. Okay. So first thing that we can do is to add two vectors. Okay. So by vectors, right now I'm just talking about some vectors in Rn. Okay. What do I mean by Rn? Rn means that the vector will have n entries. Okay. So 1, 2, n. So this is an n-dimensional vector that we say. Okay. For example, R2, so a vector from R2 would look like 1, 2. From R3 would look like uh, 1, 2, 3 probably. Okay. So you might have heard a term called high dimensional data. High dimensional data means that I'm speaking very loosely that they have many features and they are also independent in some natures. Okay. Okay. So first of all, let's talk about vector addition. Okay. So let's say if you have two vectors, A, B, C. This is very elementary. Please forgive me for those who already know it. And let's say X, Y, Z. Then the corresponding elements are added. So if you add two vectors, the first positions gets added. Okay, so it would be A plus X, then B plus Y, and C plus Z. For example, let's take a very simple example. Let's say if you have 1, 2, 3 and 1, 0, 2. If you add these two vectors, this would become 2, 2, and 5. Okay. And similarly, if you do a subtraction operation, you can accordingly work out the math. Okay. So this would become 0, 2, and 1. Okay. It's just that the corresponding elements get evaluated. Okay. Before vector multiplication, let's also look at okay, something called as scalar multiplication. So these quantities are called vectors. There is something that is known as scalar. What is a scalar? Scalars are just your numbers that you have been using forever. So scalar is something like 2 or 3. These are your scalars. Okay, we'll talk more concretely when we define vector space, what are scalars and what are vectors. But right now, let's assume that this is what a scalar is. Okay. So if you multiply, let's say a vector by 2, let's say this is 1, 2, 3, then every element of the vector gets multiplied by this particular scalar. So this would become 2, 4, and 6. Okay. This is how you multiply a scalar with a vector. Okay. Now there are two ways to sort of do vector multiplication, that is multiply two vectors. One is called as dot product and another one is called cross product that you might have done in school. Cross product are not very useful when we talk about machine learning or those kind of things. Dot product are more useful. So we are going to cover this one today. And that is what is covered in the course also. Okay, so let's say you have a vector. I think this is pretty thick. I'll make it slightly thinner. Yeah. Let's say you have two vectors. One is A, B, C. You can write it row wise or you can write it column wise. Both are fine. Okay. And if you, this is the symbol for dot product. Okay. And if you want to take its dot product with x, y, z, then this is given by, so first element gets multiplied with the first element, that is ax. Then you put an addition sign, then you add second element multiplied by the second element plus third element multiplied by the third element. This is called the dot product. Okay, I'll take an example. Let's stick to the same vectors that we used. So let's say 1, 2, 3 multiplied by 1, 0, 2. Okay, so this is given by 1 into 1 plus 2 into 0 plus 3 into 2. Okay, so this is 1 plus 0 plus 6, that is 7. So let's say if this vector was x, this vector was y, then x dot y is 7. There is one more way how people write this dot product, that is via transpose. Okay, so people also write x transpose y. This is equivalent to x dot y. Okay, why is it equivalent? If you know matrix multiplication, you know. If you don't know, we will cover it in some time, and then it will be clear why x transpose y is equivalent to x dot y. Okay, so this is how we do uh, dot product. Any doubt in this? Like if you have any doubt, because you will need a dot product at many parts when you learn machine learning. If you have any doubt, just clear it right. Okay, so well and good. So again, I'll repeat for those who joined late. If you have any doubt at any point, please unmute yourself and ask the question, or you can also type it in the chat box. Okay, so we have added two vectors. What is the meaning of dot product of two data? No, we don't have dot product of two data. We only have dot product of two vectors. Okay. So if your two data points are represented by vectors, you can talk about their dot product. But right now we are just talking about dot products of two vectors. Okay. So there is nothing called dot product of two data. Okay. There can be dot product of two data points where every data point is represented by some vector.
Yeah, one question here. So the number of dimensions should be same for both the vectors, right?
Then
Whether
only you
for
can
addition. Okay,
take the dot product. Exactly.
thank you.
Okay. Okay. Okay, so you might have heard when you did vectors in physics classes that vectors have both length as well as direction. So we will try to see some common ways how we can calculate length of vector. Uh, Vectors would be right now from Rn only. So if you have some vectors from Rn, how can you find length of that particular vector? Okay, so like let's say if you have a 2D coordinate and you have a point 1 comma 1, you know how you can calculate the length, right? So this point is called 1 comma 1. So if you join this line, this sort of forms a right angle triangle. This is 1, this is 1 comma 0, and this is 0 comma 1. So you can do this Pythagoras theorem, that is 1 square plus 1 square. Okay, and this is root 2. So this kind of notion of length is called as Euclidean length or Euclidean norm. Length is also referred to as norm when you study linear algebra. If you see word norm written somewhere, that is nothing but a fancy name for length. Okay, so this is how we calculate Euclidean length. Another name for Euclidean length is L2 norm or L2 length. L2 norm is a more common word than L2 length, but Euclidean length is a common word. Okay, so I'll formally define what is L2 length, norm or Euclidean length. So if you have, let's say, a vector x1, x2, x3, xn, this is an n-dimensional vector, then this is how you can, let's say this is x. This is how you can represent the L2 norm or the Euclidean length of the vector. This is just a representation how you can say that I am calculating the L2 length. Okay, this is given by square root of x1 square plus x2 square, so on till xn square. Similar to this, we added the square of every element and then we took the square root of that particular quantity that we got after adding everything. This is called as your L2 norm or Euclidean length. Okay. For example, uh, if you have, again, 1, 2, 3 is our common example. So L2 norm of this particular, this 2 represents the 2 in L2. Okay. This is given by 1 square plus 2 square plus 3 square. This is 1 plus 4 plus 9, which is square root of 14. So this is the length of this particular vector. Okay. One small thing that I want to draw, when you will learn regularization, there is something called L2 regularization, which is your ridge regression. I won't go into details of this. I'm just telling that if you do machine learning course, this might hit you. And there is something called error regularization that is called as Lasso regularization. Okay, I have written regression, which is not correct. Regularization I'm talking. So when you do L2 regularization, along with your loss function, if you remember, you add L2 norm of your weight. Okay, that's why it is called L2 regularization. Okay, so there, whenever you do that course, no, these are not 1 or 2 dimension. Why are they named like that? Okay, I'll tell you why are they named like that. So if you see, we take square of every term. So this power 2 is here. And after adding, so this is, if you write it more carefully, it is, and then you take power 1 by 2, right? Square root is power 1 by 2. So because of this 2 over here, here, this is called L2 norm. This is nothing to do with dimension. This is just the nomenclature that we use. Okay, yeah. So this thing that you're referring to is called mod. This generally is used for real values. For example, you take mod of -2, -3. When you talk about vector, this is a more used notation. Okay. So if you will write something like this, people will understand what you're trying to say. But at least in mathematical world, this is a more used notation. I hope, Aditya, I'm clear. Okay. So it's better to use this. This is more formal and more acceptable notion. Okay. Okay. So I was talking about L2 and L1 regularization. I just want to draw a figure that you might recall from, if you have done a machine learning class, you might recall. If you haven't done, if you do it in future, this might be helpful. Okay. So let's say this is my XY coordinate. Okay. So this is my X coordinate. This is my Y coordinate. This is my origin. Okay. I want to draw all the points that are of length 1. Okay. So length of any vector is nothing but distance from the origin. In other words, I can say that I want to draw all the points which are at distance 1 from the origin. Okay. So how can we draw? You might recall that this is given by a circle of length 1. Okay. So length of these vectors will be the radius of the circle, right? And hence it would be the circle of radius 1. So for this length 2, we will have a circle of length 2. Yeah, for length 1, you call it a unit circle. So this is a unit circle for L2 regression. I'll draw a unit circle for L1 regression also, but that won't look like a circle. Okay. So this I'm referring because there is a phenomena that when you do L1 regularization, you get more sparse weights. And why is that? That is related to this particular figure. If you do a machine learning course, then it would be clear. And this figure might help you understand there. Okay. Okay. Now we come to something called L1 norm. I'll quickly go over L1 norm. So let's say if your x is x1, x2, xn, then L1 norm is given by mod of x1 plus mod of x2 and so on. This is your L1 norm. Okay. And let's take the same vector for vector 1, 2, 3. L1 norm is given by mod of 1 plus mod of 2 plus mod of 3. This is 6. Okay. And if I draw unit circle, I won't go into very much detail. We have some more contents to cover, but I'll just draw. Okay. So unit circle over here is given by a trapezium of this form. So this is 1, this is 1 comma 0, this is 0 comma 1, this is minus 1 comma 0, this is 0 comma minus 1. So, but as you said unit circle, by unit circle we mean that all the points that are at distance 1 from the origin. So if you use this as a notion of length or the distance, then you will get something like this. Okay. Okay, so this is what I had to say over here. We'll quickly go over a generalized notion of norm. So we have till now defined two norms, that is L2 and L1 norm. We can have many norms. For every integer, we can have a norm. Okay, so that is for an integer p, sorry, I would say for a whole number p, we have a norm LP norm, which is defined by, let's say x is x1, x2 till xn. Then p norm is defined by x1 to the power p plus x2 to the power p. You add them all up to xn to the power p, and you raise it to the power 1 by p. Okay, so 3 norm would be x1 cube plus x2 cube and so on till xn cube and cube root of this. Rather than square root, now you have cube root. Similarly, for p norm, you will have pth root of the summand. Okay, this is how a general LP norm is defined. Okay, so these are some of the notions of length that you can have for a vector. Euclidean norm is the most common, but you should know these norms also. Okay, these might be helpful for you in some application or other. Okay. Any doubt in distance or this length of a norm? Then we'll move to angles. Okay. So I'll move ahead. So this is something called as angles between vector. Okay, I would just for mentioning, I would like to mention, for example, when we talked about length in our school days, we just talked about Euclidean length, right? Right now, the angle that I'm going to talk about is what we did in our school also, that is from dot product. Okay. There is a generalization of this called as inner product. So for example, the way you had many different kind of lengths, you can also have different kind of angles that you can obtain from inner product. Okay, but we are not going to cover it at least in today's lecture. Okay, And if you are interested, you can refer any of the 3 books that I have initially mentioned. There they would have defined inner product and everything. Okay, this would require some more mathematical understanding. Probably we'll do it in coming weeks, but not today. Okay, so right now let's define angle between two vectors. Let's say we have vectors x and y. Okay, then you know that dot product between x and y is also given by norm of x into norm of y cos theta. These are L2 norms. Okay, so cos theta can be obtained as this, and hence theta can be obtained as cos inverse x dot y divided by norm of x into norm of y. Okay, so I think there is a question also in this year's assignment that says that you have to calculate cos theta, right? You have to calculate 2-3 terms. So let's say you have two vectors. Again, let's stick to the same vector 1, 2, 3 and 1, 0, 2. What is the angle between these two vectors? Then cos theta is given by dot product between these two. We calculated the dot product to be 7 divided by norm of both of them. So norm over here is 1 square plus 2 square is, so the square root of 1 plus 4 plus 9 multiplied by square root of 1 plus 4. So this is 7 divided by square root of 14 into 5, right? So this is the cos theta, and if you take cos inverse, you can obtain the angle between these two vectors. Okay. Any doubt till this point? Okay. So here is a question for you guys. This is from, I think, previous year's assignment. Can you please solve and type the answer in the chat box? This is an easy question. This is so if you will solve, you will understand it better. Can you tell me the angle between these two vectors? Okay. Sir Indra, I think it's correct, but let's wait for others also to calculate. Yeah. So 2-3 people have calculated. So again, cos theta is given by a dot b divided by norm of a into norm of b. So if you calculate a dot b, this is minus 1 into 2 plus 2 into 1 plus 1 into 0, right? And then some norm of a into b. If you see the top, you will see it's minus 2 plus 0 by norm of a norm of b. So the numerator becomes 0, right? And cos 90 degree is 0, so theta is 90. Yeah, dot product is 0, vectors are perpendicular. That's absolutely correct, and that's what we are going to discuss in the next topic. So a fancy name for perpendicular vectors are orthogonal vectors. This is just another name for perpendicular vectors. So the way we defined perpendicular vectors was that two vectors are perpendicular if they are at 90 degree. Okay. By the way, I'm like, if any math student would hear me, he would not be very happy with what I'm saying. That I'm saying that perpendicular is orthogonal is just a fancy name for perpendicular. But yeah, right now for our need, we can just understand it this way. Okay. So perpendicular vectors were when the angle were 90 degree. Orthogonal vectors are, so if the dot product between two vectors is 0, then they are called orthogonal vectors. So x and y are orthogonal if x dot y is 0. Okay, this is the definition of orthogonal. And if you talk about Rn, a vector in Rn, and you talk about Euclidean norm and everything, in our basic setting, then these two definitions are equivalent, that perpendicular is equivalent to orthogonal. Okay, so again repeating, orthogonal vectors are nothing but vectors such that x dot y is equal to 0. Okay. There is something that is known as orthogonal set. So let's say if you have a set of vectors x, y, z, and you can have more, then this set is called orthogonal set if you take any two vectors in this set and their dot product is 0. So let's say you have vectors x1, x2, xn, then the set is orthogonal if xi dot xj is equal to 0 for all ij. Okay. So this is the definition of orthogonal vectors, that if you take the dot product, you're going to get 0. Okay. There is something that is also called as orthonormal vectors. So orthonormal vector uh, have two properties. First is that they are orthogonal vectors, right? And next is that the length of these vectors is 1. Okay. So x and y, if these are vectors, you will call them orthonormal if x dot y is equal to 0 and your L2 norm or whatever norm you want to use is 1. Okay. This is the definition of orthonormal vectors. One very small thing that that is very trivial, that let's say if you have a orthogonal, if you have, let's say you have a orthogonal set, right? Correct? Then you can convert it to orthonormal very easily. Okay. How you can do that is orthonormal. So let's say you have a set A, B, C, which you know is a orthogonal set. Okay. Then if you divide A by its norm, B by its norm, and C by its norm, then the overall output that you will get, this would again be an orthogonal set, but now these vectors will have length 1 because you have already divided them by their length. Okay, so you have obtained unit vector in that particular direction. Okay, so for any orthogonal set, you can obtain the corresponding orthonormal set. Any doubt till this point? Okay, so I have some time, so I'll try to explain it slightly more detailed. So Aditya, let's say if you have two vectors A and B, okay, and A dot B is 0, okay, then if you multiply or divide both A and B by some scalar, okay, let's say you have two numbers, let's say 2 and 3, okay, now if you take 2A dot 3B, okay, these would be vectors, this you would also obtain to be 0. Okay, if you multiply or divide by any scalar, for example, if you take A dot 2, A by 2 dot B by 3, this also you will always get to be 0 only. You can try this out. Okay, because when you multiply or divide by a scalar, you are not changing the direction of the vector, but you're just changing the length. So if two vectors are at 90 degree, and if you change their length, they'll still be at 90 degrees. Okay. Now what I'm saying is, let's say somebody gave you an orthogonal set. Then you know that if you take any two out of them, their dot product is going to be 0, right? B dot C is 0, A dot C is 0. Okay. Now somebody says that I've already given you an orthogonal set. You convert it to an orthonormal set for me. Okay. what does he mean? He wants that every of these vectors should have length 1. Okay. How you can convert them to a vector of length 1 is by dividing by their norm. So if you divide A by the norm of A, then you will obtain a vector of length 1. So the set that you obtain by this method is an orthonormal set. Okay. So I hope it's clear, Aditya. Okay, nice. Okay. So whatever we have discussed appear to be, for some of you might have appeared very elementary, and yeah, it was not very difficult. So are these really relevant to machine learning and things that we want to do, right? So these operations that we talked about, everything that we have talked about, these are very much relevant to the current scenario of machine learning. Okay. So the most basic thing that we saw is that this can be used to represent a data point or represent features. What is the geometric meaning of dot product? Okay. I'm not very sure about it right now, but I'll try to see what we can do. Okay. I'm not very sure, Jai Shri Pradeep. I'll try to answer your question in the next session probably, because rather than telling something that I don't know, I don't want to mislead you. But if you see by equation A dot B, so this is uh, mod of A mod of B cos theta. So like let's say if you have two vectors A and you have another vector B, right? Then dot product gives you some scaling of cos theta between the angle. So if the angle between them is theta, then this is some scaling of the cos theta of that particular thing. Okay. This is what I can comment right now. Like more I will explain it probably in the next class, or I can post it on the discussion forum if you want. And if I recall, this particular book, I think has geometrical interpretation for both dot and cross product. But it has been, I think, 7-8 years when I did this thing, so I'm not very sure right now. But I'll post it. But you can also refer to it if you want. Okay. Okay. So getting back to what we were talking, how are these relevant to machine learning? So using vectors, you can represent features of a data point. Okay, this is the first point, that how it is relevant to the modern day machine learning. Second point is, let's say when you have some features, okay, let's say, let me think of an example. Okay, so let's say uh, you have data of a person, okay, and it contains his marks in class 10, his marks in class 12, and so on. And based on this, you want to predict whether he would get a job or not. Okay, this is what this is a machine learning task that we can do, right? So if you recall, many of you would have got some marks in CGPA, okay, that is out of 10, and many of you would have got marks in percentage, that is out of 100. Okay. Now, if you recall, how do we do linear regression? So let's say this feature is called x1, x2, x3, and we assume that our 10th marks is in CGPA and our 12th marks is in percentage. Okay. So linear regression looks something like this. We want to find the values of A, B, C, satisfying some of our data points, right? If some of you have done some basic course in machine learning, you know what I'm talking about. Okay, some bias at the end. Okay, so if you have marks out of 100 and marks out of 10, the quantities for which you have marks out of 100, those features will sort of dominate your learning process. Okay, so if there is variation over here, that would be more visible as compared to when you have marks out of 100. Okay, so this is just a simple example. In real life, you can have features whose range vary a lot. Okay, so one good way to do is, so go about this is that you normalize all the features. Okay, so you convert all these marks out of 1, let's say 0 to 1. Okay, so how you can do that thing is, yeah, so what you can do is, for a particular feature, let's say you have marks out of 12, you can divide everybody's marks by 100, right? Or what you can do is, another way to see this is, you can normalize this feature. So the thing that we talked about dividing by norm is relevant over here, that when you normalize features or you normalize data points. Okay. Okay. Now there is something called word to vec CNNs, or you might know node to vec. Okay. So when you do deep learning or machine learning, you encounter a lot of vectors. That is clear, right? But if you look at, let's say, common methods like word to vec or CNN, so this word to vec, what does this do is, it will take a sentence as an input. Let's not talk about sentences right now. It will take a word as an input. And let's say we want to classify whether that word is a noun, pronoun, adverb, or this kind of things. Okay, we want to do this. Okay. Now, if you look at words over here, every word is of different length. So if you had, let's say, this linear regression, SVM, or deep learning models, whatever you apply, they have an input feature of fixed size. Okay. So how do we deal with data sets where we have inputs of varying lengths? So if you want words as an input, then every word can have different lengths. How do we deal with this? Okay. So one way to deal with this is, you convert every of these words into some vector. How do we do that? I'm not going to discuss today. That is a part of deep learning course. But what we do is, we convert these words into vectors, and then we learn on those vectors. Okay, so there also vectors are very important. So this kind of practice is followed whenever you process word data, speech data. Okay, sometimes in images too, graph data. Okay, these are the places where vector representations becomes very important. And in calculating these vector representations, you many times use your dot product as a similarity measure. So if you have dot product, you can find angle between two vectors, and if angle is close to each other, then those vectors are said to be close to each other. Okay, so there you use dot product, and then you use your length also. So these things are very much used uh, like in machine learning and deep learning community. So yeah, these things are not gonna be waste. Okay. Okay. Now we'll talk some more things about vectors. First thing is linear combination of vector. This is a definition. This is that we will define. Okay. Let's say you have vector u and v. Okay. Then alpha u plus beta v is a linear combination of u and v, where alpha and beta are scalar. Let's understand this via an example. I think it would be very clear whenever we write an example. Let's say you have a vector 1, 2, and you have a vector 3, 4. Okay. If you multiply your first vector by some number, let's say you multiply it with 2, you multiply your second vector by some other number, let's say 3, and you add them. Okay. So if you break this word linear combination, you are combining these vectors in a linear fashion. So linear fashion is you are multiplying it with scalar, okay, and you are adding it. You are not doing something non-linear, like you are not squaring these vectors, you are not multiplying them among each other, you are not taking dot product, you are not taking length, you are just adding them. Okay, so this, whatever you will obtain, is called linear combination. Okay, so you are combining these vectors in a linear fashion, and linear operations are multiplication by scalar and addition. Okay. Okay. This is something called as linear combination. There is one more thing that I think I forgot to write over here. It's span of a vector, the span of a set. Let's say you have a set containing two vectors u and v. Okay, then span of S is set of all linear combination of elements of S. So let's say I'll sort of try to write it out. So let's say my S is 1, 2, 3, 4. Then if I take all possible linear combinations, so you multiply, let's say 1, 2 by 0.1 and take 0.3 into 3, 4. And you keep changing this 0.1 and 0.3, and you will obtain different vectors. If you write these all vectors in a set, that particular set is called span of this S. So you take all possible linear combination and you write them in a set, that particular thing would be called span of S. By the way, the span of this particular set will be complete R2. You will obtain each and every vector that you can have in R2 if you take span of these two sets. Okay. Any doubt in span and linear combination? Because that is very important for understanding linear dependence and independence. Can you solve an example of span? Okay. So listing all elements of span won't be possible. Okay. I can try something. Okay. Let's say you are in a two-dimensional space. Okay, this is your two-dimensional space. And you have one vector, right? Uh, let's take this to be 1, 1. Okay, let's take this to be 1, 1. And your S now only have one element, 1, 1. And you want to find the span of this particular set S. Okay. So what's the first option that you will have? First scalar that you can think of is, let's say we multiply it by 0. And because it has only one element, we can't add anything to it, right? We can only multiply it with scalar. Keep multiplying with different scalar and you will obtain elements of your span. Okay. So multiplying with 0 would give us 0, 0. So let's use red color to represent this. Multiplying with 1 would give us this particular vector. Multiplying with half would give half, half. Okay. Multiplying with 2 would give us 2, 2. So if you keep multiplying by larger number, you will keep getting this line, right? So every point on this particular line you will keep getting if you multiply by suitable scalar. If you multiply, let's say, by a negative number, -1 into 1 comma 1, you will get negative side of it, right? They just all vector that can be found by changing scale. Okay, so okay, I'll come to your point, Jeba. So the span of this particular set would be this line in both the direction. Okay, this is one example. Now let's say you add one more vector. This was your 1 comma 1. Let's say this was your 1 comma 1, right? I think this color is visible. This was 1 comma 1. You added one more vector, let's say this. Okay, now if you added these two vectors, this complete line in both the direction will be in your span, right? This line and this line will be in your span. This line and this line will be in your span, right? Now if you take some of these two vectors, if you recall parallelogram law, you will obtain these two, this particular vector. So if you take this, say, let's say this is x, this is y. If you take 1 times x plus 1 times y, you will obtain this vector. So this will help you obtain this particular line also. Then you again take some, you will obtain this also. You again take some, you will obtain this also. You can keep adding and you will get whole of R2 as your span. Okay. Am I clear, Aditya? If this was an relevant example. So writing every element of span is not possible, but you can visualize it this way because you have to take all the combination, you can't write. So span of these two elements that I wrote, 1 comma 2 and 3 comma 4 would be complete of R2. All the vectors, all the two-dimensional vectors that you can think of would be in span of these two sets. Okay. Now somebody asked that so linear combination are where U and X are simply just all vectors that can be formed by changing. Okay. See, Jeba, whatever you have written, that is the definition of span. Okay. So span is all the vectors u that you can obtain by changing a and b when you have x and y fixed. Okay. Linear combination is just a way how you combine two vectors. That is, you are multiplying it with scalar and then you are adding it. It's just a name for the way you are combining it. What you have written, that is the definition for span. Okay. Span of x and y. Okay. Understood. Okay. Okay. So we have discussed about an hour. I think I'll give you a 1 or 2 minutes break. Let's meet at 7:03 again, and we'll discuss about this linear dependence and independence. Let's take 3 minutes break so that if some of you have something, you can take a break for 2 3 minutes. I'll start again at 7:03. Okay, I'll start again. We'll talk about linear dependence and linear independence. So linear dependence and linear independence is property of a set of a vector. So it's not associated with a particular vector, but linear dependent and independence is a property of set of a vector. Okay. So you will call a set of a vector to be linearly independent or dependent, not a particular vector. Okay. So let's say you have three vectors A, B, and C. Okay. So when we call this set to be a linearly dependent set, okay, so let me write it slightly properly. We call a set containing three vectors A, B, C linearly dependent if, now when you can call it linearly dependent, if you can write any of the vector in this set as a linear combination of other vectors. Okay. So for example, if C is equal to some alpha times A plus some beta times B. Okay. This C choice of C is not unique. So even if you had, let's say, A is equal to some alpha times B plus beta times C, then also this would have been linearly dependent. Okay. So you call a set as linearly dependent if you can write any one of the vectors as linear combination of all other vectors. Okay. So this is a intuitive way of thinking. If we formally define, so let's say, let's first look at an example, then we'll formally define. Let's say you have a set of vectors 1, 2, 3, 1, 0, 2. This is 1 minus minus 2 and 1. So if you see, let's say this is A, B, C, then you can write C as 2 times B minus A, right? That's why this set is linearly dependent. Right. Now let's define this thing formally. We'll use this particular line to define it more formally. So let's say you had C is equal to alpha A plus beta B plus C. So you can rewrite this as alpha A plus beta B minus C is equal to 0. Or you can rewrite as alpha A plus beta B plus some gamma C is equal to 0. Now the second line that you have written will cover all three equations. So even if you had B written as alpha A plus beta C, if you take B this side, then also this equation would be satisfied. If you take A this side, then also this equation would be satisfied. So we call a set of vectors x1, x2, xn to be linearly independent if there exist scalars alpha 1, alpha 2, alpha n such that alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 so on till alpha n xn is equal to 0. This means nothing, like this is the formal definition of linear dependence, but intuitively it means that you will have some vector, let's say this xk, which can be written as linear combination of all other vectors. Okay. This is the definition of linear independent vectors. And linearly dependent vectors, sorry, and linearly independent vectors is just opposite of linearly dependent. So a set which is not linearly dependent is linearly independent. So which is not dependent is independent. Okay. So you won't have these, there won't exist any alpha, alpha 2, alpha n, so that this combination can become 0. For example, okay, and there is one more thing that I missed over here. You can't choose all alphas to be 0. So you can't have alpha 1, alpha 2, all of them to be 0. Then obviously the sum would be 0. So you must have at least one of the alpha is to be non-zero. Okay. Okay. So consider this set having element 1, 0 and 0, 1. No matter what alpha and beta you choose, you can't make it 0, 0. Okay. Except for the case when alpha is equal to beta is equal to 0. Otherwise, you can't make it to be 0, 0. So this set is a linearly independent set. Okay. Another small thing. Let's say you have a set containing x1, x2, and you have 0 vector in it. Okay. Then no matter what other elements are, your set will always be linearly dependent. Why is that? You can choose this alpha 1 to be 0, this alpha 2 is 0, and corresponding to this you choose any alpha, let's say k is equal to 1, then your linear combination would get become 0. Okay. So if your set has 0 vector, then that set is always linearly dependent. Okay. Okay. So we have a lot to cover. I think I'll skip this portion. If you have any doubt in linear dependent and independent, you can ask. If we have time towards the end, we'll come back to this point. Okay. So we'll go to the next thing, that is matrix algebra, and then we have also vector space and dimensions to cover. Let's see how much we are able to cover. Okay. So vectors were used to represent one particular data point. Okay. So let's say the data point corresponding to me can be represented. Okay. Or it can be used to represent just one feature. Let's say the name of all people who have joined this session. That can be represented by a vector. But in practice, the data points that you will have is you will have multiple data points. So data set that you will have multiple data points and multiple features. So how would they look like? Let's say you will have something called name, then age, then qualification, something like this. So you will have entries here, 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 here. So now you see this was a one-dimensional representation. Now you are expanding this to a two-dimensional representation. Okay. Here is where your matrices comes into the picture. Okay. So this can be represented via matrices. So matrix is nothing but a two-dimensional representation of data. You might have seen something like this. These are called matrix. Okay, so you have not only one vectors, but many vectors stacked together. Okay. Before going to this basic operations, let's talk something about size of a matrix. Okay. So let's say you have a matrix of this form, 1, 2, 3, 4, 5, 6. Okay. So every horizontal entry, this horizontal thing, this is called a row. This is called a row. Okay. And this particular quantity is called a column. Okay. So the horizontal thing is called a row and vertical thing is called a column. Okay. And size of a matrix is written as number of rows times number of columns. This is not a multiplication sign, this is just how we represent. So it has 2 rows and 3 columns. So size is 2 by 3. You won't multiply this thing to obtain a 6. This is how it is written, 2 by 3. Okay. This is one thing. Another thing is, like let's say you are saying that this is A23. Okay. So elements of a matrix can be written in this way, A23, let's say. So what does A23 means? It means it is element of second row and third column. So second row is, let's say in this matrix, if you look, this is first row, this is second row, and first, second, third, this. So this is 6. So this 6 can also be written as A23. Okay. Again, this is very elementary, but if this is not clear, then how will you understand all those back propagation and everything? Okay. This is for someone who might have missed this in school or something like that. Okay. So this is how you write an element in the matrix. This is how you compute the size of a matrix. Okay. Now we go to basic matrix operation. First is called matrix addition. So let's say you have a matrix 1, 2, 3, 4. I'm just want to go by examples because these are elementary stuffs. 3, 4, 6, 8. Similar to as you done in vectors, you will add corresponding elements. Okay. So you will add 1 with 3. This would be 4, 6, 9, 12. This is how you do matrix addition. Okay. Next thing is scalar multiplication. You multiply every element. Okay. This is how you do scalar multiplication. This is similar to what you did in vector. Next thing is matrix multiplication. Okay. So matrix multiplication, let's say you have matrix A. You want to multiply it with matrix B. Then there is a rule that this must follow. Okay. Not all matrices can be multiplied with each other. Only matrix of special sizes can be multiplied with each other. Okay. Let's say this matrix is P cross Q. Okay. And this matrix is N cross M in size. Okay. If this Q is equal to N, if Q is equal to N, then only A and B can be multiplied. Okay. And how we multiply them, let's see. So what I said is, I want, let's say this is 1, 2, 3, 2, 4, 6, and this is 1, 2, 1, 3. Okay, I want to multiply these two matrices. So size of this matrix is 2 cross 3, and size of this matrix is 2 cross 2. 3 and 2 don't matches, so I can't multiply this matrix. Let's add one more row to it. Let's say this is 1, 4. Okay. So this is now 3 cross 2, and I can multiply these two matrices. So what will I do to obtain my first element? To obtain the first element, I will take first row of first matrix and first column of first matrix. Okay. and do a dot product kind of a thing. Okay, what I'll do is I'll do 1 times 1 plus 2 times 1 plus 3 times 1. This is 6. Okay. To obtain this entry, now this is row 1. So this is 1 comma 2th entry. So I'll take first row and second column. Okay. So this would be 1 into 2 plus 2 into 3. 8 plus 12. This would be 20. And similarly, you can fill all the entries of your matrix. Okay. Anybody who don't know what matrix multiplication is, we can spend time, then otherwise we can move to more important topics. If you don't know, this is the time, just say, because you will have matrix multiplication at many times. You will do back propagation. You will do many things where you will have matrix multiplication. I hope everybody knows. Then we'll move to something called vector space. Let's leave behind elementary things and get slightly more rigorous. I intend to do this thing, but if time permits, we'll see. Okay. So next thing is something that is called as vector space. Okay. I'll try to be very mathematical over here. I won't be intuitive over here because this is a mathematical quantity. Okay. So for a vector space, you need 4 things. Okay. You need a set of vectors. You need a set of scalars. You need a plus operation, and you need a multiplication operation. Okay. In order to form a vector space, you need 4 elements: set of vectors, set of scalars, addition operation, and your multiplication operation. This set of this set of scalars are always a field. I'm not going to go into abstract algebra, what a field is and everything. But what I can say to you right now is the set of scalar that you can choose are generally R, C, and Q. Most generally, you will always encounter R and C. R is your set of real and set of complex. Okay, so you can choose scalars only from set of reals and complex for the time being. Okay, so if you have a set of vectors, you have a set of scalars, you have defined how you can add two vectors, you can define how you can multiply two vectors. Now you will say that you just discussed how we can add two vectors and how we can multiply two vectors. But vector space gives you flexibility to define your own addition operation and your own multiplication operation. Okay, and you can still hope that you will satisfy many good properties that your general addition and multiplication operation satisfy. Okay, so let's say what properties are required to make these 4 things into a vector space. Let's say you have defined these 4 things. If this satisfies these 8, 9 properties, then this would be called a vector space. Okay, first and foremost thing is closure property. By closure property, what we mean is, let's say you have two vectors x and y. If you add these two vectors, then it should again belong to your set of vectors v only. Okay, so for example, let's say you have two vectors 1, 2, and you have 3, 4. You can't define an addition operation which makes them a vector in 3 dimension. You can't do that. Okay, so when you add two vectors, you should obtain a result within that particular set only. Okay, this is a foremost condition, and the same is true also for scalar multiplication. So if you multiply a scalar with a vector, you should obtain the result in that particular set only. This is called as closure property. Okay. Next basic property is that it should be commutative in sense of addition. Okay, so x plus y should be equal to y plus x. it should be associative in terms of addition. Okay. Existence of 0. So there should be an element. If you add that element to any element x, then you will obtain that element itself. So this is called existence of 0. So there should exist an element 0 such that if you add that thing to any element, you should obtain that element only. Okay. Next is the existence of inverse. So if you have any element x, then you should have an element y, so that if you add y to that thing, you should obtain 0. These are the basic properties that you need for this 4 things to form a vector space. These 4 properties were related to your addition. Now let's look at properties related to scalar multiplication. So these 4 were related to addition. Let's look at something related to scalar multiplication. Again, you should have an element that is called as multiplicative identity. So if you multiply 1 with x, then you should obtain x only. Okay. Also, this is called multiplicative associativity, that if you have a, b, x, if you multiply the scalars first and then multiply it with a vector, and if you have a, b, x, this should be same. This might appear very trivial to you, that all these properties are already satisfied by R2 and those kind of things, whatever we have discussed till now. But understand that if you define some operations on your own, this plus operation and multiplication operation, this gives you a power to define your own operations. Okay, and that too, it will satisfy many property that your normal addition and multiplication operation satisfies. Okay, and it also gives you an ability to add, let's say, polynomials, or define this kind of operation on functions. How do you multiply two functions? How do you add two functions? So these kind of properties it has. Okay, so we'll see some examples. Okay, last two properties are called distributive properties. So if you multiply by a scalar x plus y, then it should split. If you add the scalars first and then multiply by a vector, then also it should split. Okay. So these are some 7-8 properties that you always need not remember. Okay, only when you are defining something, you can open a book and verify these properties whether these are satisfied or not. If you have mathematical background, then you would remember that this forms a abelian group with respect to addition, and then it satisfies just these two properties with respect to multiplication, and distributive properties with respect to both of these. Okay, so we'll keep this list in our mind and let's see some examples. This is a simple example. We're going to do some more non-trivial examples. Okay, let's look at this example. So let S be a non-empty set and F be any field. F, this script F denotes set of all functions from S to F. Okay, so S is some non-empty set, F is some field. So the script F is a set of all functions from S to F. Okay. Two functions are called equal if they are same for all the values of S, that is understood. Okay. Then they are defined operation such that F plus G, if you add two function, then you compute the values at individual levels and then you add them. Okay. And if you multiply them by some scalar, if you multiply this function by scalar, you first evaluate the value and then multiply it by that particular scalar. Okay. This is how they have defined addition and multiplication, and they have asked us to check whether this is a vector space or not. Okay. So again, if you look at these properties, okay, I'll sort of try to do all the properties one by one. This is going to be again slightly trivial. Okay. So first property that I said you must verify is closure. Okay. So Now, if you look at this thing, f plus g is a function which takes input s, right? So it is a function from s, and where does it go? So this value is in f, this value is in f, so their sum is also in f, because f is a field. I'll just assume that. So I'll just say that if you have two elements in a field, then their sum is also in the field. So f plus g is also a function from s to f, so it would belong in this particular set, script f, right? So closure is satisfied with respect to addition. Also with respect to multiplication, this element is in f, the c is in f, so their product is also in f. So again, the product is also a function. So this cf is a function from s to f. Okay, so this is closed under addition and multiplication that they have defined. Okay, now let's look at other properties. Is it commutative? Yes, it is commutative. Now f plus g, this is equal to f of s plus g of s. Now elements in field are always commutative, associated everything. When you reach the field, you can assume that it has all the properties that is possible for R. So this is equal to g of s plus f of s, which is indeed equal to g of f of s. Okay. Similarly, you can verify that it is associative. Now about existence of zero element. We'll next look at existence of zero element. So what we want is, let's say we have f of 0. We want this to be f of s. This is what we want. Now this is equal to 0 of s. Okay. What we want this to be only f of s. So this element should be 0. So 0 of s is defined as 0 for all s. So if we have a function that maps everything to 0, that function serves as a 0 function for this particular setup. Okay. Then what would be inverse? Inverse for f of s would be, let's say, minus f of s, which gives, okay, so f of s inverse is minus f of s for all s. Okay. Okay. What is the next property that we had? We are done till 4th. Next is vector scalar multiplication. That is very obvious, because 1 would be multiplied over here and you will get f of s1. Somebody raised his hand. You can please unmute yourself and speak, or type it in the chat box. No, we are not assuming it for the sake of proof. It is given that f is a field and our set is set of all functions from s to f. So f of s that you will obtain would always be in the field. We are not assuming anything for sake of proof. It is mentioned in the question, because this f is a function from s to f. So f of s that you will have, that would be an element of f, and f is given to be a field. Okay. Somebody raised his hand. I think it was by mistake, or if it wasn't by mistake, you can unmute and or type it in the chat box. Okay. And similarly, your other properties can be verified. This is not a very difficult thing. The thing that I wanted to say is that you just don't have one notion of addition or multiplication in terms of vectors. This is a generalized notion that you can have. Okay, so there are some set of properties that if you satisfy, you can have your own definition of addition and multiplication. Why am I talking about all these things is, okay, let's take a small detour. I think this is a course on essential mathematics for machine learning. Let's talk about machine learning for a bit. Okay, I'm assuming that you have some very basic idea about machine learning. Okay, but even if you don't have, just those who don't have any idea about machine learning, just remember this thing. Most of the machine learning method, okay, what they do is they try to approximate a function, okay, from, so they will try to learn this function which is from some Rn to, let's say, some R. They did Rm, let's say. This is more generalized. So we just try to approximate this function from set of data points that is available to us. Okay. When you have this n fixed, so you know the length of your input vectors, you have many great algorithms. For example, your SVM or basic deep learning like multi-layer perceptron. Okay, all these methods are available to you, or whatever methods you have learned, logistic regression, linear regression. These methods are available when your n is fixed. Okay, but as I mentioned a few moments ago, there can be type of data sets where your size is not fixed. Okay, what you do in such scenarios, let's say we are talking about words. Okay, you want to learn something on words. Words can have different size, length of the words. So for example, this has 5 length, this has 3 length. How will you input it to your model? Because your model can only accept data point of fixed length. Okay, in such scenarios, what we do is we convert this to some Rn, and these vectors are then called embedding. You might have heard of term called embedding, or even these transformers use this thing, the very famous transfer that are getting these days, they also use these embeddings. Okay, now how do we do embeddings is, what we want is, let's say this is your space of words, this is all your words, this is hello, can, girl, boy, these are all words. We want to convert this to some Rn. This is our mathematical space. Okay, so in Rn you will have some vectors, you will have this vector, this vector. What we want is, if two words are close to each other in your English dictionary, for example, father and mother, they are close to each other, right? Then what we want is, the vector that we get corresponding to father is close to the vector that we get corresponding to the mother. Okay, or vice versa. Let's say good and bad are opposite of each other. Okay, so what we want is, the vector that we should get for good and the vector that we should get for bad should be very far from each other. Okay, now I have been loosely speaking that words which are close over here should be close here. Okay, now what do we mean by this close? I'm very loosely speaking that they are close to each other. This can be in terms of distance between them. Okay, this close can be in terms of angle between them. Okay, so what is the notion of closeness that you have to choose based on your application? Okay, in some application angle might work, in some application distance might work, and in some application none of them might work. Then in such scenarios, you might want to define your own addition and multiplication. So by multiplication, you can have a new notion of angle. If you redefine your dot product, you can have a new notion of angle. And based on that, you can define your similarity. Okay, so if you are working on some application where these methods are not working, and you have some intuition that if I define similarity in such a way, if I define an angle in such a way, this might work. Then you might need all these list of rules that I have mentioned over here. Then you might check whether these are applicable. Can I do further operations on them or not? Okay. And as I have started discussing this, I'll just mention one small thing that here I told you how you can define closeness between vectors. That can be in terms of angle or distance, or you can suitably define it on your own. In word2vec, generally what they do is they have a large corpus of word. They have a large document. Let's say they have a collection of documents. If words appear together, let's say uh, size, okay, so for example, data and point, if you will scan through all these documents, there would be many points where data and points will occur together, or data and set would occur together. So words that would occur together, not just after each other, maybe at a gap of one or two. Okay. So let's say data, some set. These are also considered to be close. Okay. So if these kind of things happen, then we call them close in the word space. Okay. And this thing is not only true for words. There are many kind of data that can be processed in similar way. For example, speech data. Okay. So when you say something, the duration can be large or small. Okay, based on that you have different waves. And to process that, again, you will have to convert them into some vectors. Then also you will have this notion of angle, distance, those kind of things. And then again, you can curate it according to your need. Was I clear whatever I said in that? Or did anybody have any doubt? Wants to ask? Okay. Now we will quickly go over something that is called as subspace test. Okay. So what is a subspace? So let's say you have a vector space. Now we know that we have a vector space. So you already have these operations. Okay. Let's say W is a subset of V. Right now we are just saying that W is a subset of V. We call W a subspace of V if W also satisfies all properties of a vector space corresponding to these operations. So operation will remain same, but we want this subset also to satisfy all the property. Now, because we satisfy all the property itself, you need not check all the property, all list of 9 property. Okay. If you only check this particular test, this is called subspace test, that let's say if X and Y belongs to W, and for every C and B, if Cx and By belongs to W, then W is a subspace. This is called subspace test. Okay. So we have a quick example. Okay. This I think would make things clear. This is your original vector space. This is R3 over R. And this is usual addition and multiplication. There is nothing fancy over here. Now W1 is a set. Okay, so one more small thing. If you take C is equal to B is equal to 0, then this also means that 0 belongs to W. Okay. And most of the cases when you do these kind of questions or examples, you will see that 0 does not belong to W, which will help you prove that it is not a subspace. Okay. So let's see now. XYZ contains all XYZ such that X minus Y minus Z is 0. Okay. Now let's take another element. So this, let's say XYZ and ABC belongs to W. Okay. Now what does this mean? That X minus Y minus Z is 0 and A minus B minus C is 0. Now if you take alpha times XYZ plus beta times ABC, this would become alpha X plus beta A comma alpha y plus beta b, comma alpha z plus beta c, right? So if you see, if you multiply this thing by alpha, wait, let me see. If you multiply this equation by alpha, this equation by beta, okay, and you add these two equation, you can obtain that alpha x plus beta alpha minus alpha y plus beta b minus alpha z plus beta c is equal to 0. So if you have x and y, if you have x, y, z and a, b, c belonging to W, then alpha this plus beta this is also an element of W. So this is a subspace. Okay. Similarly, you can show here. No, you can't show here. Okay. So let's see what is wrong with W2. W2 says x, y, z such that y is greater than x. Okay. What has happened here? Yeah. No. Now it's fine. Y is greater than x. Okay. Let's say x, y, z and a, b, c belong to W. If we take alpha is equal to -1 and beta is equal to 0, then alpha times x, y, z plus beta times a, b, c, what is it equal to? This is equal to minus x minus y minus z. And we know that if y is greater than equal to x, then minus y would be less than equal to minus z. Sorry, minus x. So this property does not hold for this particular combination of sum. Okay. So this would imply that W2 is not a subspace. So if you have a question where you have to check whether a set is subspace or not, you should just check this particular property. Okay. Other two would be subspaces. Okay, we have little time left. Okay. Another definition for vector is that elements of vector space is called vectors. Okay. Okay. So I'll quickly go over this basis and dimension. I'm not sure if I'll be able to complete it in time, but at least I'll try to give something. Okay. So first of all, let's talk about what is a basis. When we discuss span, we saw that if we took span of set 1, 2 and 3, 4, this was whole of R2, right? So when we try to find basis, we look for similar sets. Okay. So what do we want to do is we want to find the set S, okay, such that span of that set is equal to the complete vector space V. Okay. So we want to search for a space such that span of that particular set is whole of S. Okay. Also, basis has an additional property that if you take any subset of this particular set, let's say, yeah, somebody has to say something. Mangal, you have to say something. additional property that this satisfies is, let's say if you have a proper subset of S, that means you remove any element of S, okay, then you can't span the complete set V. In some sense, this is the smallest set which can span your complete vector space. Then that set S is called basis of your vector space. For example, if you look at this particular example, this 1, 2, 3, 4 spanned your complete set. Mangal, you have to say something. But if you remove even one of these vectors, then you won't be able to span your complete set. Okay. So in short, basis is something that is your smallest spanning set for your vector space. Okay. And let's take example and let's try to find out some of the basis. So for Rn over R, okay, so another thing is that basis need not be unique. Okay. So you can have more than one basis. For example, this 1, 2, 3, 4 was a basis. You can also have 1, 2 and 1, 0. This is also a basis. But one thing that would be fixed is the number of element in the basis. So you can have different bases, but all of them will have same number of element, and that number of element in basis is called dimension of vector space. Okay. So let's talk about Rn over R. So Rn over R have something that is known as standard basis. So let's talk about R2 over R first. So R2 over R, we just look at two bases over here. The standard basis is given by 1, 0, 0, 1. This is a basis for R2 over R. Similarly, for Rn over R, the basis is given by 1, 0, 0, 0. Then in the next one, you will have second element as 1 and everything as 0, and so on. So this is a basis for Rn. Okay. So yeah. And number of element is called the dimension. So for R2 over R, the dimension is 2. For Rn over R, the dimension is n. Okay. Okay. So this set is called PNR. Okay. So what is this set? This is polynomial up to degree n. Okay. So what do I mean by polynomial up to degree n is? So you can, let's say, polynomial up to degree 3 is all the polynomials with maximum degree 3 or less. Okay, so x cube plus x square plus 1. This is all the polynomial up to degree 3. Okay, so this also forms a vector space. Okay, its basis is given by 1 x square xn. So you see that P and R has n plus 1 elements in its basis. So its dimension is n plus 1. Okay. I don't think I can cover this thing. I'll skip this part, but I'll cover something that I think might be useful to you. This is matrix multiplication, a different approach. Okay. Just a second. Why am I not able to expand it? Just a second, I'll reopen it. Okay. So the whatever I'm discussing now, that is inspired by a lecture by Professor Gilbert Stein from MIT. He has discussed this in his lecture very beautifully. And this approach might be useful in understanding matrix multiplication at many places where you can't explicitly multiply and look at every element. Okay. So the first thing that we're going to discuss is, let's say you have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and you want to multiply this with a vector. Okay, let's not do this. Okay, so you have a matrix where you have some entries. Okay, okay, sorry, I forgot to share. I'm really sorry. Is it visible now? I hope it should be visible. Okay, okay. See, I didn't do much. Okay, so let's say you have a matrix whose first column is C1, second column is C2, third column is C3. Okay, so it has 3 columns and it can have as many rows as you want. Okay, let's say I want to multiply this matrix by a vector called ABC, just multiplying by a column vector. Okay, so what does it mean when you multiply it with a column vector? So if you would have gone the usual way, what you would have done is you would have taken the first row, then multiplied it with the column, then you would have obtained the first element, then you took the second row, multiplied and obtained the second row, right? This is the usual approach that we take. Okay. But there is another way to look at this multiplication. What is that? So when you multiply a matrix with a column, what you are doing is you are multiplying first element of your column with first column. So you are doing A times C1, then you are doing B times C2, and then you are doing C times C3. And then you are adding all of them. Okay, so let's verify this whether what I'm saying is true or not. Let's look at example of 2 cross 2 only, 3, 4, and you multiply it with 1, 2. If you would have gone the usual way, you would have multiplied this first row with the first column, and what you would have obtained is this is 1 and 5. Then you would have gone this row and this thing. Then you would have 3 plus 8, 11, right? Now let's do what I said. Okay, so what I'm saying is 1 multiplied by the first column. So this is again a linear combination of columns of. So if you multiply a matrix by a column, you are taking linear combination of its columns. Okay, and 2 multiplied by 2 comma 4. Okay, so what does this become? This become 1 3 plus 4 8, which is 5 11. Right now we multiplied by a column. Let's look at what does it mean when you multiply a matrix by a row. So this is R1, this is R2, this is R3. Okay, you can't post multiply by a row because the size of this row is 1 cross 3 and this matrix was something cross 3. So then matrix multiplication won't hold. So you can only pre-multiply by a row vector. Okay. Okay. So again, this would mean, so what would be the output? The output would be a single row. Okay, if you pre-multiply by a row. So this would mean that you multiply A with the first row, then you add to it B multiplied by the second row, and C multiplied by the third row. Okay. This is another notion of multiplication of a matrix by a row or a column. Okay. Now let's look at what it means. Let's say I have C1, okay, C2, C3, okay, and I want to multiply this with another matrix which has column B1, B2, B3. Now we know if we multiplied this matrix, right, with just this particular column, then we would have obtained something using this, that we would take linear combination of all the columns using the elements present in B1. Okay. So if you do that, you will obtain first column of your output. So let's say the first column of your output is D1, then D1 is given by this C1, C2, C3 multiplied by just your column B1. This you know how to do, right? You just take the linear combination. And D1 is given by that. Similarly, to obtain D2, you multiply your complete matrix by just column B2 and you will obtain D2. Okay. Sorry, this should be this. Okay. And so on. This is how you can visualize matrix multiplication in another way. Okay. So if you remember this, this might help you in visualizing when you do back propagation or those kind of things in deep learning course. Then sometimes this kind of visualization also helps you understand how you went from one step to another. Okay, because explicitly calculating every element and writing it becomes tedious sometimes. Okay, so okay, I'll stop the recording first.